Good morning, friends. Today we are going to discuss about design of gating system relevant to the casting process. The design of gating system is important. The reason is, if proper gating system is not designed, not implemented, defective casting will be there. Casting molten metal will not reach to the cavity appropriately in the desired way. So what happens? It will be a short casting and it will be a defective casting. So one has to be judicious in order to design those gating system. There are many uncertainties whenever liquid molten metal is poured into the system for casting. The flow has to be ensured, and there are a lot of problems, a lot of choking area possible if it is not done appropriately. So the first part of those gating system is the pouring basin. Why the basin is there? Because it has to be worked as a reservoir of material so that the continuous flow is maintained. So extra material will be provided whenever there is a shortage. It will ensure the continuity of the flow. So that is why a pouring basin has to be there, because appropriately putting all those things synchronized from the ladle and flowing through that continuity is sometimes not easy to maintain. So better to give in a buffer like basin, and from the basin will subsequently, appropriately, uniformly, it will ensure the flow. So from the pouring basin, the first part of it, which is look like a basin, and from there itself it will enter into the sprue. Sprue will be just the angle, cylindrical, or it is a cone, and that will ensure the continuous flow of the molten metal, and from the sprue itself it will enter into the runner with the gate, and then it will go for the rectangular channel that is called runner, and down part of the sprue there is a sprue well. So take the extra material which is covered, which is unable to go into the gate, so that will be stored in sprue well, and that will act as also a buffer. So extra material and other things, they will not percolate, and from the feeling of it they can also supply if the extra material is there. So well is also a good strategy to take care of the uniformity of the flow through the gate system, and then to the channel, and this channel will provide those entry through the gates, and there are in gates. Previously that was an external gate, and then from the channel to entry of the cavity, that is called in gates. The first, from the sprue to the runner, there is a gate, and there is also a gate from the channel to the cavity, and these are called in gates, and many cases those in gates and other things depending upon the volume of the casting. The problem is that as for the higher melting point metals, they will solidify very, very fast. They will take all those, they will lose heat to the atmosphere very, very fast, and there is also a possibility of solidification in different channels. So we have to ensure that the fluidity, otherwise if any part of those channel or gate it is solidified, then they will act as a blocking agent of the further flow of the molten metal, and this is very detrimental for the casting. So what is happened, sometimes some ingates, parallel ingates are ensured, so that the different part of the cavity, it will take no time in getting those material and get solidified. An entire thing has to be done in a hurry, in a hard time demand system. Otherwise there is a possibility of the solidification starting, and once solidification starts, it will act as a blockage, just like hard block. The blood cannot be flown through the arteries and veins, and it will be a problem of the cause of the heart attack. So here heart attack will not be there, but the problem will be that molten metal will not reach to the nook and corner of the cavity, and ultimately the casting will be defective and casting has to be rejected. So all those things in one go, very fast, and appropriate design is crucial. So one can find it out, the basic elements of a gating system. The top part is pouring cup, from the basin to the pouring cup, and then sprue, it is a cone, and from the cone itself it is a down sprue. People tell also down sprue, and pattern also has made in order to prepare a space for those sprue in the mold, and down sprue or down grade, from there itself sprue well is there, and from there itself the rectangular channel well through the molten metal flows, and from there itself with ingates in multiple direction concurrently fade into the main cavity of the casting. This is the very standard time tested configuration of those gating systems, and what will be the height of the sprue, what will be the diameter of those sprues, what will be the taper and other things, that has to be gone to the finer details, but basic configuration of design is like this. So the functions of the gating system is, a gating system controls mainly mold filling process, how the molten metal will enter into that, and why it is critical, because it is done at elevated temperature. And at elevated temperature there are many problems. One is immediately that can be solidified, so the flow will be a problem. The problem is that the periphery level, the oxide formation will be there, and if those oxides are also traveling along with the molten metal in the periphery, it will cause problem, and ultimately that will result in the inclusion defects associated with those casting. So everything has to be done in a defined time period, and gating system controls the mold filling process appropriately. And the main function of the gating system to lead clean, because it should not be inclusions, it should not be oxide, clean molten metal from ladle, where it will be transported from the furnace to the casting cavity, ensuring smooth, hassle-free, no turbulence, uniform, continuity, and all those things are there with complete filling, so that no difficult part of the casting cavity is hungry of molten metal. So complete filling, and hence to design a good gating system one must know the behavior of the fluid flow. So there comes out to be the question of understanding the fluid flow behavior, and we have a very handy software now that is called computational fluid dynamics, which can help us to understand the behavior of the fluid flow, behavior of the molten metal at elevated temperature in those kind of geometric constraints, how they will behave in order to fill the cavity of the mold appropriately. So the basic elements of gating systems are, the first one is pouring basin as a buffer, then the sprue well, then rectangular channel that is called runner, and from runner it is ingate, and the sequence of flow from molten metal to the ladle in this direction serially. So one can see those sectional view of cope and drag configuration. These are the different pouring basin. We can see there are from the pouring basin the sprues are there, and then these well is there, and from their gate itself, from the gate itself it goes through runner, from the runner it is feeding all those intricate cavities of the mold and restricted by the cores of the casting, so that the hollow formation in the casting is done, and it is a typical open cope and drag formation, and there are some placements of open risers as a sensors, whether the intricate part is not hungry of the molten metal. Then the vents are the things that provided for the escape route of all those entrapped gases, and entire container is called flask, and in between cope and drag it is separated by a parting sand, that is the parting line, and all those things are represented very properly in these sectional view of Cope and Drug configuration. So pouring basin, it is the funnel shaped opening made at the top of the mold, just like a funnel or a basin, and this main purpose of the pouring basin is to direct the flow, take those things from the source and direct it through this channel of sprue, molten metal from the ladle to the sprue. That is the role of pouring basin. And it should be made substantially large to keep near edge of the mold box, as near as the mold box, and so that it is a very big reservoir, so that there is no shortage of those flow of the molten metal, unless the entire part of the cavity is completely filled. So basin must be deep enough to reduce the vortex formation. So vortex formation will create some kind of turbulence, and which is not at all associated with, because all those vortex and other things, if it are allowed, they can jeopardize those intricate overhanging portions of those mold cavities. So vortex formation has to be limited, so it has to be large enough to reduce the vortex formation and kept full during the entire operation, because if it is not full, there is a possibility of vortex formation. So filling the entire part of it, you will restrict the vortex formation, and which is an intended one. Next is sprue. It is a passage which connects pouring basin to the runner or inlet, and it is a cone. Slowly and steadily it is increasing the pressure of the flow, and that is why it is a cone shaped, and it is in between those basin and to the runner or inlet, and generally made by tapered down to avoid aspiration. Of all those aspirations are very detrimental effect in case of casting, so prevent it. And cross section of the sprue may be square also, some cases rectangular or circular. Circular is popular, and according to that it will be a feeding channel. So round sprue has a minimal surface area exposed. More the surface area, the better, higher possibility of solidification. What do we don't want the things at the sprue will solidify fast. The spring, all those things will solidify last, because it solidify fast, it will restrict the flow of the molten metal. And in order to ensure that, we need, according to Chauvinov's rule, we have to restrict the surface area. Surface area to volume ratio has to be favorable. So volume should be big, surface area should be small, and whenever we can go for those kind of cylindrical part of it, it will be favorable on the basis of that. Round sprue has a minimal surface area exposed to the cooling, offers lowest resistance to the flow of materials, because less possibility of solidification, so smooth flow will be there. The square or rectangular sprue sometimes minimize the air aspirations and all those turbulence, so it is sometimes compromised with the different geometrical shapes. Sprue well is the bottom part of the sprue, and it is located at the base of the sprue, and it is free fall of molten metal through the sprue and by right angle towards the runner. So it is just like a wicket keeper. Take the extra part of it and ensure that the flow is smooth, and the extra flow, it will be kept in the sprue well. And the cross gate of the runner, it is cross gate because crosswise it is there. So in case of large casting, the fluidity length of the molded metal is less than the maximum distance. Yes, that will determine by the fluidity index. The fluidity index is that in a spiral way from the sprue itself, it is found out that what length, after the sprue is full of molten metal, at what length it solidifies, and the length will determine the fluidity. More the length, more the fluidity, and many cases of those length is more than that of the fluidity index. It will solidify before that. So what people have to do, they have to do concurrent channels. So less than the maximum distance required to be traveled, so molten along with the full path. So we have to create some kind of multiple inlets. Concurrently the feeding has to be carried out to reduce the maximum flow distance. even the flow distance is big. So multiple way we can attend that, so that the mold cavity is not in shortage of the flow of molten metal in a sustainable manner. And for another utility of the cross grate or the runner is that a multi-cavity mold also, each cavity must be at least one ingate. In many of the castings you have multi-cavity, so each and one should be one ingate, and it is necessary to concurrently fill a common passageway coming from the common passageway of those molten metal, which is finally linked with the sprue to complete the flow path. Flow path up to sprue and all those passageway, it is the same, but it is strictly divided into the cavity specific ingates, concurrently filling for those things, so that there should not be any short casting. Short casting is a very, very difficult casting defect arising due to the non-reach of the molten metal to the very, very difficult corner of those casting cavity. So the passageway is called runner, this parallel one, and cross section of the runner is usually rectangular to get a streamline. Rectangular has a fluidic behavior, it will resist, it will have streamline flow with less turbulence. So that is necessary to have laminar or linear flow without having turbulence, because turbulence are very deadly and detrimental. The turbulence will jeopardize the intricate shapes of the mold cavities, especially in the overhang portion. So turbulence has to be avoided as much as possible. So runner must fill completely, it has to be filled completely before letting the molten metal enter the ingates. So stage by stage, full-fledged filling, and then it will enter into the other part of it to ensure that the solidification takes place from the directional way. And in casting where more than one gate is present, the cross-sectional area must be reduced, because it will be a flow drop. So in order to ensure the proper flow, the area must be reduced after each gate, and amount may be the area of those ingate to ensure uniform flow, because whenever multiple ingates sequentially, the flow will be reduced. So as with the product or with the reduction of the flow, the ingate designs and their area has to be minimized, so to ensure the uniform smooth flow. Ingate or gate, it is a small passage which contains a runner to the mold cavity, from the runner to the mold cavity, and that channel is known as, that transportation place is known as ingate or gate. The cross section is square, rectangular, trapezoidal. So different kind of sections will be there, and according to that it will be fed in order to minimize the turbulence. And there are different classification of gating systems. There are many. So orientation of the parting line, the gating system can be classified as horizontal and vertical. The gate is horizontal and vertical, depending on the demand of the casting and position of the casting. In horizontal gating system, parting plane is horizontal. In vertical, parting plane is vertical. So horizontal parting plane is horizontal and contains runners and ingates. That plane is contain runners and ingates. Sprue is vertical, but gating is horizontal, and sprue is perpendicular to the parting line. And these are suitable for flat casting, where the flat part is associated with the casting, it is suitable for, and as in green casting and gravity die casting, so that by gravity the cavities and all those things are filled by the molten metal. So this is known as horizontal gating system. And there are another variety, vertical gating system, parting plane which is vertical, parting line is vertical and contains runners or ingate. So every time you have this gating system contains runners or risers, but the only thing is that it is vertical because plane is vertical. And for gravity filling process with high pressure sand molding, and the sprue is vertical. For pressure die casting, sprue is along the particle line. So whether it is gravity feed or a pressure fit, and according to that the gating system will be designed and is suitable for all sorts of castings. So one can say these gating system. The first one is the top gate, it is entering from the top molten metal. The second one is the intermediate one, it is the bottom one. So molten metal enter through this bottom part of the cavity. So it is called bottom gate, and parting line, whatever it is entering into the molten metal, all those gating system entering into the cavity in the parting line itself, that is known as bottom parting gate. And all those things people have found it out what are the choke area depending on the top gate, bottom gate or parting gate, and according to that the decision will be there, care has to be taken. So classification of horizontal gating system is top gating system, bottom gating system and parting line gating system, and that can be seen by this. The left one is top gating system. So molten metal is entering from the top of the mold cavity. In case of bottom gating system, the molten metal is entering from the bottom part. And for the parting line, wherever the parting line gating is, that as far as along the parting line the molten metal is entering into the mold. So these are the three differences. They have their pros and cons, and definitely the geometry specific, where you have to put top, bottom or parting line type of gating system. And there are filling related defects, and there are many. I have already told that 27 standard defects are there in sand casting, and there are many defects are associated with these gating systems and liquefactions associated with those process, and this is known as one, incomplete filling. Incomplete filling is a very difficult task because some part of the mold is very hungry of the molten metal, and at last they are deprived of the molten metal. So what results? Incomplete filling. Then the second is solid inclusion. Solid inclusion source can be oxides at the time of melting, and some oxide formation will be there with the atmosphere oxygen related contamination of the metallic parts, or it can be created because it is the turbulent flow, it is responsible for breaking down the intercavities of the mold, and whatever broken down they remains there and they will act as a unwanted inclusion. This is called solid inclusion. And the third one is, as there are elevated temperature associated with those casting process, lot many gases will be produced, and if those gases are not appropriately vented, venting is a very important operation after the entire part of the molding is done. If it is not appropriately vented, the problem is that gas also entrapped, and that will create a bubble and weakness of the casting. Whenever the gas will be liberated after part of it, already the casting is lost. So incomplete filling, it is caused by poor fluidity. That is why we are so concerned about the fluidity of the molten metal, and results in cold shut or misran. And that is the result of it. And it occurs when two streams of molten metal coming from the opposite directions meet. Cold shut occurs when the two streams of molten metal coming from the opposite mix, and then suddenly it solidified, keeping some gap. So this is known as cold shut. And the misran occurs when the hot molten metal does not fill the thin or end section properly. So that is also incomplete filling, that is known as misran. Those thin sections are hungry of the molten metal, even to the waiting for the last for the molten metal, and the waiting for Godot is not over there for the cavity, and that way it results in the misran. That is also a standard defect of sand casting. One can see those cold shut in terms of the figure is a discontinuity that appears on the surface of the cast metal as a result of two streams of liquid meeting and failing to unite. There are some borders between two countries, and those borders are refraining them to shake hand with each other, and that also happens during casting, whether for the cooling and solidification. Before that they cannot meet, and that is the cause of cold shut. And it is a fault in the surface of a piece of metal caused by two streams of molten metal not joining properly. So that is the problem that is known as cold shut. Then solid inclusion. It is caused by high turbulence of the molten metal during filling in the form of sand from the intricate overhanging portions of the cavity just broken down and included in the casting. Not wanted for, uncalled for intervention of the molding sand in this molten metal, and that is called inclusion, solid inclusion. Sand inclusion occurs due to bulk turbulence, so that is why turbulent flow is restricted. Turbulence is a deadly phenomenon in the cavity because it can jeopardize all those intricacies of those mold. So turbulence in the gating channels resulting the erosion from the sand. Sometimes gating channels and all those things, there also come those inclusion, and they will flow and get it solidified. That will place in solidification as the one type of defects. And slag intrusions are caused by surface turbulence along the path of the molten metal, and some times these oxides are also coming into that take place, and that is the cause of all those defects. Then filling related defects of all those things, very good representation. The left one is cold shut, mesh run, blowholes, all those things, gas entrapment and the gas porosity. Gases are entrapped and not properly vented, so they remain there and create those defects. So gaseous entrapments are also a very big concern for the casting. So air entrapment appears in the form of blowholes. They stay there, and whenever they are relieved, they will make a mark. They will put their stress there. So they occur when air or gas inside the mold cavity cannot escape through the molding and gets trapped in the final casting, and they made their mark, and that is a big defect. So major sources of gas evolution include dissolved gases in the molten metal, vaporization of the mold, moistures, combustion of the binders, all those molasses and other things. At elevated temperature, they start liberating gases, and gases cannot find the escape route. And the reason for the gas entrapment is high as gas generation rate, poor permeability. That is why permeability of the sand is required, because highly permeable sand will allow those gases to escape even in a very before solidification, and that will result in the correctness of the casting. But poor permeability of sand, filling and solidification of molten metal too fast. So fast that the gases cannot vent through those things, and poor venting of the mold, and all results in these kind of gaseous entrapment. And gaseous entrapment to get sound casting, this is the biggest problem of that. Sound casting cannot be obtained if those gases are entrapped, and has to be properly controlled, and this can be obtained by a well designed gating system. We can discuss about some of the vacuum casting, where the possibilities of the air entrapment and other things are less, because all those things will be done steering and then with suction. That is why people are going for the vacuum casting, so that these kind of entrapment of the gases and other things are little bit less. Another classification of these ratio of the total cross section area to spray through exit, and that is a mathematical one, and one can represent all those things in terms of ratios, and according to that they can decide. Cross sectional area of sprue exit, and cross sectional area of the runner, and cross sectional area of the ingate, and those things are represented by A suffix S, A suffix R, A suffix G. So that is the ratio of the time, and we can find it out which is the best possible ratio to implement that. And see all those pressurized gating systems and different kind of ratios associated with that. And the pressurized gating system is that the pressure is given so that the fluid will enter into that, so there is less concern about short filling, those problems and defects due to short filling of those casting process. So choke, another part, is also there in some of the castings are there, but here with the pressure one can find it out that no intricate part of the mold is hungry of molten metal. So I am not going into that details. So non-pressurized or gravity fed type of gating systems, and another is non-pressurized gating systems, and the choke and other things have their relationship associated with that. No point in going in a short introductory video of those detailed parts of those choking strategies, choking happening, and strategies to prevent that. That's all for today about those things. Thank you.